Let me see if I haven't seen her in a while.
Let me see. I haven't seen Janet forever.
Let me see.
Pull up a picture.
I have a picture of Claire.
Claire.
I don't know how many pictures. Let's see. Let's see if Instagram has any. She never posts though. Jenna's horrible.
I feel like she knows.
Don't worry. She'll have some wedding pictures we can show you all soon.
Oh, what?
Wait, what did you say? Did you say wedding pictures?
It's coming any day now. I swear.
I didn't think
There's
Jenna-
her profile
I didn't think
picture,
Jenna was gonna be
but
the
it's
one.
got to be like 3 years old at least.
That's gonna be new to me though. I haven't seen Janet in so long.
Aubrey wasn't expecting
What's her
Jenna
name?
to stay married.
I know.
She never like talks guys.
Looks like yeah.
What kind of boyfriend she had?
First
She
one,
tied
Okay, so let's
She's like,
let's
"Oh,
take a look
patient.
here.
I don't want to do this again.
All right, what can we do? What can we do with
Oh, is
this?
she? Oh yeah, that's my cousin.
We can find
That's
the
a better
symmetry
picture.
and we can
Yeah.
find the domain.
Domain is all real. Domain's all reals,
Yeah.
isn't it? Yeah. Domain's all reals.
Yes.
We'll come back and talk. Did anybody want to suggest what the symmetry might be for this?
Neither.
Neither?
Yeah.
Even.
It's either neither or odd. That's my
Okay, so we got them all covered here. Well, let's go back in hindsight and see if we can explain why we get the symmetry we get on this one. Let's go ahead and just dive into some derivatives. How about?
Okay.
So what's our first derivative here?
2x to the negative 1/3,
Okay,
which we can rewrite that if we
good.
wanted to.
Minus.
2x.
Okay, and if we want to rewrite that, we could, we got a couple of ways we could do this. We could write them as fractions and get common denominators, or we could factor out, let's just do that. We haven't done that in a while.
Yeah.
What if we write this as 2 over x to the 1/3 minus 2x?
That's what I was thinking.
So we'd like to get this to be a fraction, right? Have a rational look, where it looks like has a distinct numerator and denominator, so we can find the critical numbers more easily. Remember how we do that? Critical numbers where the derivative equals 0, we get from the numerator, right? Zero's in the numerator. Places where the derivative is undefined, we get from the denominator. So what would we have to multiply top and bottom by here? X to the 1/3. Good, so we're going to multiply by x to the 1/3 over x to the 1/3. And then we get 2 minus 2x to what power on the top? 4/3 over x to the 1/3, if we want to write it as one big fraction. Okay, so critical numbers. Where is our derivative undefined? At 0. Everybody agree? Okay, because that gives us a 0 of the denominator. So y prime is undefined at x equals 0. Okay, now what about zeros of the function? How'd you get that?
Because 1 to the 4/3 is 1. So then you multiply it by 2.
Very good.
And then 2 minus 2 is 0.
Okay,
Bottom's
good. So
still 1.
we're going to look at the numerator here, aren't we?
Yeah.
Right. We want to know, when is the numerator 0? Okay, so y prime equals 0 when the top is 0. In other words, when 2x to the 4/3 equals 2, right? Which occurs when x to the 4/3 equals 1. Okay? Solutions of that. Are there solutions of that? How would we solve that? What do we do here? Rewrite it. We could. Okay, so there's one thing we could do. Yeah. This is probably good review for us. So we could rewrite this as a cube root of x to the 4th, right? Or we could rewrite it as a cube root of x to the 4th. Okay, I'm gonna suggest maybe the bottom way might be okay. They both would work. Let's use that bottom way. If I want to solve for x, what would I do to isolate that x? Got to cube both sides to undo the radical, right? Everybody agree? Okay, so if we cube both sides, now we got to be careful when we take both sides of an equation to a power, we might introduce extraneous solutions. So we'll have to check everything. Go back and check everything prior to cubing both sides. But we'll just check everything back in our original equation right there, right? Okay, so if we cube both sides, we get x to the fourth equals 1 cubed, which is 1. Now what? How do I undo that? Fourth root. Okay, but what's my rule? If I take an even root of both sides, what do I have to include? Plus or minus, right? Can we get that? Okay. And we can do that in 2 steps if we wanted. We could say x squared equals plus or minus the square root of 1, right? If I just square root both sides, I get x squared equals plus or minus 1. I could try both of those. If x squared equals 1, that's going to give me the solutions x equals plus or minus 1, right? X squared equals -1 gives me no real solutions anyway, right? It's going to give me some imaginary solutions, but we're not looking for those, right? We're doing real analysis. We're trying to find what the graph looks like in the real plane. So this one gives us nothing. Okay, so we get the solutions plus or minus 1, which we could feed back up here and check. Do they work? If I plug in +1, well, yeah, +1 to any power is 1. How about -1? Cube root of -1 is -1, right? To the fourth is 1. Everybody agree? So they both work, right? If we plug those in, they both are satisfied. They both satisfy that equation. Okay, so is there a way we could have done this without all those steps? How could we have done this in 1 step? If I want to get x by itself, in 1 step, how could I undo taking x to the 4/3 power? How do you undo, like, again, I'll give you a little hint here. Is there a way, could I raise both sides to a power? What power would I need to take x to the 4/3 to end up with the result x to the 1? 3/4, right? If I took both sides to the 3/4 power, does that make sense? Okay, but if I take something to a power that has an even denominator, that's equivalent to an even root. So what would I have to include? Plus or minus. Do you everybody get that trick? How you can do that, right? If I take both sides to a fractional power, if the denominator is even, I just have to include my plus or minus. And so I get x equals plus or minus 1 to the 3/4, which is plus or minus 1. I can do it in 1 step. Okay, make sense? We good with that? Okay. All right, so we got our critical numbers. Second derivative. Let's keep working our way down.
Okay.
And we want to just go from here, don't we?
Yeah.
Okay. And this is a pretty easy derivative, isn't it? I mean, we don't have any quotient rules or product rules, so it's really pretty easy. What's y double prime?
-2/3 x
To the
-4. No. Right? Yeah,
-4/3.
-4/3.
Good.
-2.
-2. Okay, so where is that going to equal 0? So y double prime equals 0 when?
X equals that whole thing, -2/3 x, all that equals 2.
Right, okay, so when, we could say this, when 2/3 x to the minus 4/3 equals -2,
Yeah,
okay?
where did oh, never mind, I see.
Right?
I see.
Because those two terms have to be, right, that term has to equal, 2, not -2, you're right. Oh, no, that, we have a negative there to begin with. Everybody see that? Right, we have -2/3 x to the minus 4/3. So this whole thing must equal -2, so I get -2. Here, let's do it this way. How's that?
Good.
That better?
Yeah.
When that whole first term equals 2, so they subtract to 0, right? Okay, so then what's that give us? That gives us -2 over 3x to the 4/3 equals 2.
So that means the
Right.
bottom has to equal 1, right?
So say it again.
So that means the denominator has to equal 1 for it to be -2. Like
Has to equal
3x to the
-1.
4/3
Yeah.
has to equal 1.
Yeah, here's another cool little algebra trick. If you have a ratio, you guys know this trick where you can trade positions diagonally. You guys know that trick? That's a pretty cool one. If A over B equals C over D, I can exchange diagonally. That means A over C equals B over D. It's a pretty cool little trick. It's just a combination of, a couple algebra maneuvers. But so if we do that, then that tells us that 3x to the 4/3 equals -1, right? So x to the 4/3 equals -1/3. And so what would we have to do here now? Is that possible? How come you're right? How come that's not possible?
Because that's complicated.
Because look, the numerator is a 4, right? That means that that's equivalent to the cube root of x to the 4th power, right? Anything to an even power is always going to be non-negative, right? So is the second derivative ever 0? No, and we could show that. Like if we graph it, we can just prove it to ourselves. If we look at this second derivative function,
What do we do on this?
if we look at this second derivative function over here, there's our second derivative right there, right? Okay, let's graph that. What's going to happen on the graph? Can you tell me? This is kind of a common thing we do in math, where a lot of times we use graphs to do some analysis if we have technology available.
Well, it'll have a y-intercept.
So is it going to have an x-intercept? No, it's not, is it? It's never going to equal 0.
But it will have a y-intercept.
It'll have a y-intercept
At 2.
where x is 0. Yeah, -2.
Oh, yeah.
Yeah, good.
Sorry, I was looking at the phone. Whoa.
Never going to cross the x-axis, is it? Right. So we already demonstrated that. So this thing it's got no zeros of the second derivative. So really all I have here are just my first derivative critical numbers. Okay.
So we have no points of inflection.
And right, we can't have any points of inflection because the second derivative is never 0. True. Okay.
So does that mean that all the critical numbers of the first derivative they'll all be like going the same direction? Like they'll all be positive or they'll all be negative?
Yeah.
So
Yeah, right. The
Our-
concavity
Yeah.
can never flip. You're right.
So it's-
And you guys tell me from the graph, what's the concavity going to always be?
Negative.
Negative, right? There's a graph of our second derivative. We could pick any test point we want, and we will. We'll try all these test points. And what we'll find is that the second derivative is always negative valued. So no matter what this function is always going to be concave down. Okay. All right. So let's see if we can, I'm going to cut and paste a little bit here because it's getting pretty messy, and we'll make our table. Oops.
Oh, no, what's up?
Okay, so here's our original function. We need that, right? We need our first derivative. Oops, I'm going to pick, this is a pretty convenient form of our first derivative. So let's pick that one. Okay, there it is. And we need our second derivative, which we have right there. There they are. Okay, let's go ahead and make a table. I'll grab a pre-made table. How's that sound? Okay, we said domains everywhere. We had first derivative critical numbers at 0. What happened to 0 again? You remember?
It's undefined.
Undefined. Okay, so go down to the first derivative row, undefined. And then we had plus or minus 1, right?
Yeah.
1, negative 1. Those were zeros of the first derivative. And so what would we want to do here?
We would want to test our critical numbers.
Test our critical numbers, yeah.
With the second derivative.
With the second derivative. Okay, so we know at these points we have horizontal tangents. Okay, can we test our second derivative here? Can't. You're right. We can't there, right? Because the second derivative, remember the definition of a point of inflection is, well, how do I say this? The second derivative test, here's how I say it. The second derivative test only applies for zeros of the first derivative. What's going to happen at a critical number of the first derivative where it's undefined? If that results in an extremum, characterize the extremum. What's going to be interesting about it? It's going to be sharp, right? Can a sharp extremum have a concavity at that point? No, it can't, right? Because the second derivative, by definition, has to be undefined there, right? You can only take the second derivative could only exist or be defined in places that are in its domain. What's the domain of the second derivative? Every place where the first derivative exists. If the first derivative doesn't exist, you can't differentiate it there. Does that make sense? So takeaway from that is second derivative test does not apply there because the first derivative is undefined. We'd have to use a different test for that. But we could go back and use the first derivative test, for example. Okay, but we can't apply it here to these two. If we evaluate our second derivative at 1, what are we going to get? Well, 1 to the negative 4/3 is what? What's 1 to any power? 1. So I get negative 2/3 minus 2. Would you agree it is negative there? And has to be there too, doesn't it? Right? Negative 1 to the negative 4/3 is going to be 1 over negative 1 to the 4/3. Because the top is even, it's positive, right? Think what that is. The cube root of negative 1 is negative 1 to the 4th is positive 1, right? The numerator is even, the outcome is positive for real numbers. So then these are negative, so what's that telling us? These are both going to be maxima, smooth maxima. How am I going to know what's going on at my critical number at 0? Test points, yeah. So throw some out. What could we do for test points? Like, will be some values I could use as test points?
Are you talking about in between 0 and 1?
They'd have to be, yeah, right, they'd have to be in between, exactly. That's my point, is that the test points have to fall between critical numbers. So we have to pick something like 1/2 and negative 1/2, something like that. So if we evaluate our first derivative, okay, what's that going to give us? At 1/2, let's see, what are the signs going to be? So on the top,
Positive.
yeah, what is 1/2 to the 4/3? Is that, let me ask you this, is that going to be a number bigger or smaller than 1?
Small.
Yeah, it's going to be smaller, isn't it? Right? How do you know that? How could you justify that? How do we know that 1/2 to the 4/3 is going to be less than 1? True or false? Would 1/2 to the 4/3 be between 1/2 to the 1 and 1/2 to the 2?
Yes.
Wouldn't it?
Yeah.
Everybody agree? Right? What's 1/2 to the 1?
1/2.
What's 1/2 to the 2?
1/4.
Okay, right, that makes sense?
Yeah.
Okay, so then we know that if this number is going to be less than 1, 2 minus 2 times a number that's less than 1 is going to be 2 minus something less than 2, isn't it? Which makes the top positive. The bottom is going to be what? 1/2 to the 1/3, positive or negative?
Positive.
Positive. Okay, so we get positive there. What about a negative 1/2? Top's going to act the same because look, that's an even function, isn't it? X to the 4/3, right? Doesn't matter what I plug in there. If I plug in positive 1/2, I got the cube root of 1/2 to the 4th. If I plug in negative 1/2, I get the cube root of negative 1/2, which is negative, sure, but when I take it to the 4th, it's positive, right? Agreed? So the top stays the same, but the bottom becomes negative this time, right? The cube root of a negative number is negative. So that's negative. So what does that look like? Well, what does that look like then? What's going on at that critical number? Minimum. It's going to be a sharp minimum, isn't it? Yeah. So it's going to look something like, I'm not going to put in any concavity, but it looks like that. Well, actually, the concavity, we do know what it would look like. What is the concavity? It's negative. So I could be a little more accurate. It's going to look like that. Agreed? That make sense? Okay, so we got everything we need. If we just anchor this with some points, we got this. What's the value of my function at 0?
0.
0. So there's a point, right? What's the value of my function at 1? What's 1?
2.
1 to the 2/3 is 1. Yeah, so it's 2, isn't it? Right. So I get 3 times 1 minus 1 squared, 2. What's the value at negative 1?
2.
2. Yep, it is, right? Because that's even, so I'm going to get the same result and that's even, isn't it? So what do you think? What's going to be the symmetry here? Even,
Dang,
right?
I have
Because
three
that counts
choices
as
and
an
I got
even
them.
term.
Both my guesses wrong.
We get that. That counts as an even term because it's got a 2 on the top and that's even. So both of the two terms are even.
So in determining symmetry, do you look at the numerator of the fraction?
Yes. Yeah, you look at the numerator.
Dang it.
Okay, so then we ought to be able to graph this thing, right? We've got, if we're going to graph this, it just looks like I've got a point here at 0, 0. I've got a point at -1, +2. So up here somewhere. I'm not going to make it to scale. +1, +2. And what's it doing? What's the end behavior going to be? What's the leading term of that? It's not truly a polynomial, but what's the dominant term in that function? First or the second one?
The second one.
Second one. How come?
Because it's greater.
Because it's got a greater exponent, right? So the second one's the dominant term. It's going to act like a negative x squared function. Well, doesn't that just look like this, right? That's negative even behavior.
Yeah.
Remember that stuff? So then we know that the limit here is going to be -infinity. The limit here is going to be -infinity. And so we got this thing, right? It's just going to look like
It's like a huge parabola, but with a flip.
like that.
It's an M.
Kind of.
That one you're gonna do in your airplane.
That make sense? Okay.
Little.
Little questions on that. What parts of that? Is this stuff, like, is this stuff over here where maybe you're just feeling a little unsure about it? It's just the algebra of rational exponents, that kind of stuff?
Those are a little, I feel like I'm starting to understand those more.
Okay, good.
Just,
Sometimes derivatives get hard.
Yeah,
Just keeping everything separate.
Yeah,
It's so
just-
intense for no reason.
remember this step right here, right? Remember the step where if I'm trying to solve, this is really a key one, right? This saves a lot of, like, you can do this in one step if you just remember the rules. If I want to solve for x, I'm going to raise both sides to the 3/4 power, right? But if I'm taking 3/4, I'm taking an even root, so I have to include a plus or minus. Well, 1 to any power is 1. 1 to the 3/4 is 1, but I just have to include that plus or minus because of what I just do. Whatever. That's us. Because of this, right? Because that's a 4th power, we need that plus or minus. So that's how I got those two critical numbers. Okay? Make sense? And then, of course, we can just go back and check them. We go back and check them in the step before I raise both sides to a power, and they both work. 1 or -1. If I plug them into this equation, they're going to check. Do you even have to do that stuff? Because, I mean, your intuition pretty soon is just going to tell you, well, okay, what are the only possibilities here? 1 or -1, and they both work. You could probably just look at that and see the solutions, right? Like, I don't think you'd have to justify that on an AP test or something. You would just say the solution, so x equals plus or minus 1, and you'd be fine. Okay. How about the second derivative? When we took the second derivative and we wanted to show that it had no zeros, well, we said this equation's probably fine. How do we know that this is going to have no zeros? Remember when we solved for x to the 4/3? We got x to the 4/3 equals a negative. Again, the reason that can't work is because this means non-negative, right? A rational exponent with an even numerator is non-negative, can't be negative, right? Because you're taking it to an even power. And so that means that's impossible. No solution. No critical numbers. Okay, good. Shall we? Man, we've covered a lot. This is pretty good. You guys have seen lots of different looks here. That look familiar?
Yeah.
There's our picture. Just what we got, right? Picture for posterity for our notes. Okay, and then the last example. Oh, you know what? I put that in the wrong page. Got to go after. There we go. Okay, last one. Let's look at one with the trig function, and that's
Just
it.
throw trig in there, I get so
And then
lost.
we have hit every possible. Man, we've hit lots. And then you're good. Okay, so what about one like this? Domain.
All roots.
Is it?
Sure.
What part? There's a red flag here. What part is telling us not all reals?
Cotangent.
Cotangent. Yeah, cotangent is what?
Oh, isn't it not outside of 1 or 0?
It's reciprocal of tangent. Think of it in terms of cosine over sine, right? Cotangent is cosine over sine. So every place where sine is equal to 0, cotangent would be undefined, right? Does that make
0
sense?
and pi.
Okay. So we got to think unit circle then. So on our unit circle, where is sine equal to 0?
0 and pi.
0 and pi and 2 pi, all the integer multiples of pi, right? Okay, so I wonder if we should, let's see. Tell you what, let's take this, let's limit the domain a little bit, because this can have an infinite number of discontinuities. So let's enforce a domain. I think that's what I meant to do on this. Let's go from 0 to 2 pi. Okay. So on that domain, we would have to exclude 0, pi, and 2 pi, right? So really, that can't be our domain. Our domain would have to be replaced with 0 to pi, pi to 2 pi. Make sense? If we look at one lap of the unit circle, that's our domain for this function. Okay? All right. Now what? Could do a symmetry test, but let's not bother. Right? We don't really,
Yeah.
symmetry is useful, but we don't have to have it. What's the first step?
Take the derivative.
Take the derivative. There you go. Okay, so what is y prime?
2
2.
plus.
What's the derivative of cotangent?
Oh my gosh.
Negative
Secant squared.
Negative secant tangent. No, you almost had it.
Secant squared x.
Well, the derivative of tangent is secant squared.
Cosecant squared x.
So the derivative of
Oh.
cotangent is
Cosecant.
negative
Cosecant.
cosecant squared.
Jeez, how many guesses will it take?
Okay, so if we write that in terms of sines and cosines, that looks like 2 minus 1 over
Sine squared.
sine squared x, right? So that's gonna, so what happens then? So y prime equals 0 when 1 over sine squared x equals 2, right? Agreed? Okay.
So then sine squared x has to equal
1/2, right? Yep. Y prime equals 0 when 1 over sine squared x equals 2. So sine squared x equals 1/2. So what is sine equal? What am I doing to solve for sine there? Okay, I'm seeing this. What's that mean?
square root
Square rooting both sides. Okay, so if I square root both sides, I have to include a plus or minus.
1 over
Right.
square root of 2.
and I get 1 over the square root of 2, if I rationalize that, isn't that the same thing as, well, 1 over square root of 2, which is plus or minus square root of 2 over 2? Does that look familiar?
Yeah.
Aha. Okay,
Oh my gosh.
so square root of 2 over 2. So where on the unit circle do we get signs equal to plus or minus square root of 2 over 2? What angle do we associate that with, square root of 2 over 2?
Pi over 4.
Pi over 4, exactly. So it's going to be positive and negative, so we're going to get one there and one there. Those are the positive places where we get square root of 2 over 2. Here would be the negative places. So what are between 0 and 2 pi in our domain, what would those places be?
Pi over 4.
Pi fourths?
3 pi.
3 pi.
3/4 pi, good.
5
5/4 pi,
7.
7/4 pi, good. Okay, so those would be our critical numbers. Okay.
4 critical numbers.
Okay, that's where our y prime is 0. Where is y prime undefined?
That equals.
When sign is 0, right?
Yeah.
Okay, but are those in our domain?
No.
No, those are the places we had to exclude from our domain, right?
Yeah.
Okay. So another way of saying this, right, would have just been like saying x cannot equal 0, pi, or 2 pi. Those are our excluded values, right? Okay, good, good. Let's do a second derivative is going to not be very fun, is it? Second derivative.
Okay, we can do it.
We can do it. I like that can-do attitude. That's good.
Yeah.
No, we can't.
Okay. Let's see.
Just like Bob the Builder. You guys probably don't remember Bob the
So the
Builder.
2 cancels itself.
I watched a lot of Bob the Builder with my kids, but that was probably
Okay. Cosecant squared x. Can we separate that into cosecant x squared?
Okay, so yeah, the derivative of 2 is 0, right?
Yeah.
The derivative of cosecant squared. This is a chain rule deal, right? What's the outermost layer here? Squared. I have hand squared, right? The
Yeah.
derivative of, we have negative out front. The derivative of hand squared is
2
hand. Now the derivative of cosecant is,
it's
So what's the
negative
derivative of
sine,
secant?
negative sine x.
okay, well, what's the derivative of secant?
Oh, it's sine.
Secant tangent.
Oh my gosh.
Cosecant, cotangent.
There you go, right?
Oh my
So it's
gosh.
negative, the
Disgusting.
co-ones are
This is
negative,
gross.
right?
Disgusting.
Okay, which makes that positive,
And bar.
right? And that gives us a cosecant squared. Okay, so we get,
So we just got it back after we just got rid of it?
well, kind of, but it's also being multiplied by a cotangent now.
Oh my
Okay.
gosh.
Now that looks ugly, but what would be way easier to do is just write that in terms of I'm telling you, this is always the way to go. Write it in terms of your basic trig functions, sine and cosine.
So,
Cotangent is cosine over sine, cosecant is 1 over sine, so isn't this the same thing as 2 cosine x over sine cubed x?
yeah,
Okay, so it's 0 where cosine is 0. Okay, where is cosine 0?
at, pi halves and 3 pi.
Pi halves and 3/2 pi on our first lap, right? We're just doing one lap here
Yeah.
in a circle. Okay, so, yeah, so then, okay, so we got everything, right? That really wasn't so bad. The trig stuff, I know people hate the trig stuff, but the unit circle just makes it all so much easier, right? Just draw a unit circle up there and you know what you're doing. Okay. All right, tomorrow we finish this one up and then I'm done with this stuff.
Okay. Me too.
But then we take the test.